We are going to look at finding the domain and range of composite functions. In this first example, we have f of x equal to 2 divided by x minus 1 and g of x equals to 4 divided by x plus 3. We have two rational functions, and we're asked to find the domain and range of g of f of x. The first thing I like to do is find the domain of the first function, or the inside function. So I'm going to find the domain of f first. Looking at f of x, you could see that x cannot equal to 1 otherwise you'll be dividing by 0. So this domain of f of x is x cannot equal to 1, and other than that, it can be all real numbers. Next, we're going to find the composite function, and we're going to find its domain, and then we're going to combine it with the domain of the first function. So let's find g of f of x. The first thing I like to do is I like to rewrite that as g of f of x. This way, it says to me that we're going to go to g, and everywhere we see an x, instead of x, we're going to plug in f of x. So let's do that. We're going to have this composite function g of f of x is going to be 4 divided by 2 over x minus 1 plus 3. So here, if you compare before and after, before we have a yellow x down here, and after we have a pink version of f of x. Let's go ahead and simplify this rational function by multiplying top and bottom by x minus 1. When we do that, in the numerator, we're going to have 4 times x minus 1. And in the denominator, we're going to have 2 plus 3 times x minus 1. And when we simplify that and combine like terms, we're going to end up with 4 over x minus 1. And we're going to have 3 over x minus 1/3. Now let's find the domain of this composite function. Well, it turns out the x value that would make this denominator 0 is x is not equal to 1/3. Okay, folks, so now we have the domain of the first function, which is x cannot equal 1, and we have the domain of the composite function, which is x is not allowed to equal 1/3, and we're going to combine these two domains. So the domain that we're going to evaluate to find the range of this composite function is as follows. X cannot equal 1, and it cannot equal 1/3. In other words, this is the more restrictive of the combination of the domain of the first function and the domain of the composite function. Now that we have the domain of the first function combined with the composite function, we're going to use this combined domain and apply it to the composite function to find the range of the composite function. We already have the domain of the composite function. Now we're going to find its range. Folks, the easiest way to find the range of any function is to graph it. Excuse me. So let's go ahead and graph this rational function. Okay, the first thing we notice is that this function has a degree of 1 on the top and a degree of 1 on the bottom. Therefore, we're going to use the ratio of the coefficients out in front. So we know that this graph is going to have a horizontal asymptote at y equals 4 over 3. Next, we're going to look for any vertical asymptotes, and we see that when x equals positive 1/3, we will have a vertical asymptote. Next, we're going to look for any zeros. We could see that we're going to have a 0. The numerator becomes 0 when x equals 1. Okay. We're going to go ahead and we're going to start plotting our graph, and then we're going to use a sign analysis of the function to help us fill in the gaps. Okay, here is our horizontal asymptote at y equals 4 over 3. Here is our vertical asymptote at y equals 1/3. I'm sorry, x equals 1/3. And finally, we're going to put a 0 at x equals positive 1. Okay, so we know the graph is going to cross positive 1 in this location. Next thing we're going to do, folks, is we're going to do a sign analysis. We're going to create a little number line here with 3 critical points. The critical points are always going to be your vertical asymptotes, which in this case is 1/3, and any zeros you might have. We're going to create 3 zones, zone 1, 2, and 3, and we're going to put representative values of x into our function to determine what the sign is. Okay, so for zone 1, let's use x equals 0, and we're going to plug it into this function. If we plug x equals 0, we will see that the top will be negative and the bottom will be negative. So whenever you have an even number of negatives, the end result is going to be positive. So we know that this function is going to be positive in this zone. Here, between 1/3 and 1, we're going to use an x value of 2/3. And we're going to plug that in. Again, we don't have to know the actual value, but we just have to know the sign. So here, if we put 2/3 minus 1, that's going to be negative. You multiply by 4, that's going to be negative. So we're going to have negative in the numerator. And here, if you have 2/3 in x in the denominator, 2/3 minus 1/3 is positive, times 3 is positive. Here we have an odd number of negative signs, so that zone, the function will be negative. And finally, in zone 3, we're going to plug in x equals 10, and we'll see that 10 minus 1 is positive. That makes the numerator positive. 10 minus 1/3 is positive. That makes the denominator positive. So the entire function will be positive in this location. Okay, so now we have some more information. The other thing we could do is find the y-intercept. So the y-intercept is going to occur when x equals 0. When x equals 0, we're going to have the following function. Let's do that over here in white. If we have x equals 0, we're going to have 4 times negative 1 over 3 times negative 1/3. That's going to give us negative 4 over negative 1, which is going to equal positive 4. So we're going to utilize that this is our y-intercept at 4. Again, all we did was plug in x equals 0. That's the easiest way to find the y-intercept. Okay, so let's put all of this together. We find that when x is less than 1/3, our function has to be positive. It has to be above the x-axis. So we're going to use our horizontal asymptote and the vertical asymptote to have a graph like so. Then we're going to come in zone 2, and we're going to notice that zone 2 has to be negative in this zone. Now, zone 2 is from x equals 1/3 to x equals 1, where it becomes positive again. So here we are negative in this zone. This is zone 2, between 1/3 and 1. Then we have a 0, which we anticipate, and then the graph becomes positive and accommodates the horizontal asymptote as x goes to infinity. Folks, this is therefore your graph. Now, if we want to find the domain and range of this graph, we have to look in the areas that accommodate this domain. So we know x cannot equal 1 because of the fact that x equals 1 violates part of the domain. So we are going to take this 0, which would have been part of the normal function, but because it's a composite function, we are going to erase this 0, so to speak, by making it an open circle. So this point right here, x equals 1, y equals 0, will not be part of the range. So now that we have our graph, we're going to go ahead and document the final range thereof. So we could see here that the y values extend down to negative infinity. They go all the way up to positive infinity. So the only y values that are missing are y equals 4 over 3 because this particular graph does not cross the horizontal asymptote. Some graphs do, but this one doesn't. And we know that we had to eliminate the y value when x equals 1. So our final range is going to be the set of all real numbers such that y is not equal to 4/3 and not equal to 0. Again, the y value when x equals 1 has to be eliminated from the range. And we graph our composite function shown here. We have a vertical asymptote at x equals 1/3 in blue. We have a horizontal asymptote at y equals 4/3 in green. And we have this point removed because x cannot equal 1. In our combined domain, we see a y-intercept of 4. One thing I forgot to mention is the fact that our vertical asymptote has a 1 as an exponent, making it odd. Then as we approach the vertical asymptote, it's going to be, the graph is going to head in opposite directions. So here, this red graph, as we head towards the vertical asymptote from the left, is heading towards positive infinity. And here, as we're heading towards the vertical asymptote from the right, the y value is heading towards negative infinity. It could have been the opposite, but in other words, it could have been from this side going positive and then from this side going negative. But the fact that that is an odd exponent means they will approach it in opposite fashion. If, however, that was a 2, then you would have the graph approaching positive infinity from both directions, for example. Let's now move to our second example, and we're going to use the same two functions, f and g, but we're going to do the reverse. We're going to do f of g of x, and we're going to find its domain and range. So here we're going to get the domain of the inside function g, and in the interest of time, I went ahead and did some work ahead of time. So if you look at the domain of g, which is the first function, we find that its domain is x is an element of all real numbers such that x is not equal to -3, because x equals -3 will render that denominator 0. Let's now move to the composite function. We have f of g of x. Everywhere we see x, we're going to plug in g of x. That results in this compound rational function here. We're going to multiply top and bottom by x plus 3, and we're going to simplify, and we're left with this composite function. We're going to get the domain of the composite function, and that is going to be x is an element of all real numbers where x is not equal to +1. So the final domain that we're going to use to determine the range of the composite function is a combination of this function, this domain of the inside function and this domain of the composite function. So our final domain for f of g of x is going to be the set of all real numbers. X is an element of all real numbers such that x cannot equal -3 and it cannot equal +1. Okay, we're going to now utilize this final domain to determine the range of this composite function. Let's now find the range of our composite function by graphing it. We're going to apply this final domain to determine our final range. Here's our function right here. We see that we have a horizontal asymptote at -2. These are both first degree in the numerator and the denominator. Therefore, we take the ratio of the coefficients. Our vertical asymptote, x equals +1, because that renders the denominator negative. And also, this is an odd exponent, so the graph is going to approach this vertical asymptote in opposite directions. Finally, we have a 0 at x equals -3. We put the 0 and the vertical asymptote on our little number line here to do a sign analysis. We're going to use this green version of our function to do the sign analysis. Folks, we don't need the 2 there. We're not interested in the actual value. We're interested only in the sign. So let's go to zone 1 and let's plug in x equals -5 as a possible input in this zone. If we have a negative, We put -5 in here. That's going to be negative. We're going to have negative in the denominator. So that's 3 negatives. That's an odd number of negatives. Therefore, the graph is going to be negative in zone 1. Moving to zone 2, the easiest thing within that zone is to plug in 0. We're going to have a negative, we're going to have a positive, and then we're going to have a negative. This is an even number of negative signs, so our graph is going to be positive in this zone. And finally, in zone 3, sorry, my pen got thin there all of a sudden. We are going to utilize 10 to plug that in. When we plug in 10 here, we're going to have that first negative. We're going to have a positive and a positive. That's an odd number of negative signs, so it will be negative. Notice, folks, this negative sign appears first in each analysis. Okay, we're going to take all this information now, and we're going to go ahead and plot our graph. Now that we have all of our important data points, let's go ahead and put this together and graph the composite function. One thing, folks, I forgot to do was to get the y-intercept. Recall, to get the y-intercept, you let x equals 0. So you put your thumb on any x that you see because that's 0. That numerator becomes -6. The denominator becomes -1. -6 divided by -1 is +6. So that is going to be our y-intercept. Okay, putting this together and keeping in mind what our sign analysis told us, we find that to the left of -3, our graph is going to be negative. We have a horizontal asymptote here. We anticipate coming through that 0 and the y-intercept, and then approaching that vertical asymptote. That suggests our graph is going to do something like this. Now, because the graph is approaching this vertical asymptote and heading towards positive infinity, we're going to use that information and do the opposite. So we're going to come down here and we're going to respect the horizontal asymptote, and this is our initial graph. That should be going through the +6, so I apologize. That big dot there is y equals 6, x equals 0. Okay, now folks, we have to look at the final domain and eliminate any x values that might currently be included. We see that x equals +1 is not on our graph because we have a vertical asymptote there. However, look at this, x is not allowed to equal -3. Therefore, we have to eliminate x equals -3. So we're going to come here and we are going to eliminate this. And we're going to put this as a open circle here, and this will not be part of the domain, the range. So putting this all together, our final range up here on the upper right of the graph in blue, our final range for the composite function is going to be that y is an element of all real numbers such that the y value cannot equal -2. That's because of the horizontal asymptote we have here. That is eliminated from the range. And we need to eliminate the y value when x equals -3. Recall, x equals -3 is not part of the domain. We find the y value. The y value at x equals -3 would have been 0. So we have to take that out of the range. Folks, this is your final domain, and that's your final range for the composite function. And real quickly, let's go to Desmos and take a look what we have here. I've graphed the composite function. You see we have a horizontal asymptote at y equals -2, vertical asymptote at x equals +1. There's our y-intercept. Here's our origin here. You have our graph negative in this area. Once it hits x equals -3, it becomes positive. And here, the graph becomes negative again to the right of x equals +1 and hugs the horizontal asymptote. In terms of our range, we remove y equals -2 because of the horizontal asymptote, and we're going to remove y equals 0 because the final domain excluded x equals negative 3.